I want us to have a quick little discussion on what an atom is versus an ion, and then this idea about molecules versus compounds. So the atom, the building block of matter, if you will, it's composed of two parts, arguably. Can you guys tell me what two parts the atom is made up of? One more time? No. The atom? Some atoms are nonmetals, some atoms are metals. So they've got protons, neutrons, and electrons, but what are the two fundamental components of the atom? Good. Our nucleus and the electron cloud. The nucleus has all of the mass. And the nucleus is positively charged. The nucleus only has protons and neutrons. It's actually a lie to say that it has all of the mass, isn't it? Electrons do have mass, and they're not in the nucleus, but their mass is so insignificant compared to the mass of the protons and the neutrons. So this has all of the mass. The other component, the electron cloud, makes up all of the size. Atoms are mostly empty space. I think I gave you guys this analogy, right? That if an atom were the size of Colorado, the nucleus would be the size of a basketball, which just means the rest of Colorado is full of electrons flying around, and not really full, right? Just has electrons flying around in that space. Okay, that's our building block of our atoms. What are ions? Yeah, charged species. Oops. And why are ions charged? How could we put it into words? It's not always because they won't have a full shell. Did you say won't or want? Sometimes ions do have full shells. Sometimes ions don't have full shells. Sometimes species with full shells aren't ions. But I like this train of thought. What's the fundamental reason that an ion is charged? Good. They're charged because the number of protons is not equal to the number of electrons. And for the most part, we're not going to touch the number of protons. You've got a carbon atom, you want to make a carbon ion, you're not going to change the protons. You're going to change the electrons surrounding it, yeah? So it's all about the electrons, really. Electrons make up all of the size, which is why electrons are responsible for all of the bonding, because they're at the exterior of the atom. Electrons are what give us our ions, because they're the easiest things to take away and put into our atoms. All right, now this debate. What is the difference between molecule and compound? Is there a difference? Are they just two different words that mean the same thing? You want to take a stab at it, Ella?
One way or the other, like all molecules are compounds, but not all compounds are molecules, or like vice versa or something.
I had that same discussion last night with OChem 1, and I think that Venn diagram, like all squares are rectangles, but not all rectangles are squares, I don't think it quite works here. I tried it, but I think they overlap a little bit, but it's not the fully encircled one. Do you know what I mean? Like I can draw a circle around this, and then draw a circle that also includes this. Sarah?
Molecules are like 2 plus atoms, and then compounds are 2 plus atoms.
Wonderfully said. Brilliant. A molecule needs at least 2 atoms. You can have a molecule of oxygen, O2, a molecule of hydrogen, H2. We'll deal a lot with elemental halogens, Br2, Cl2. A compound has 2 or more elements. O2 is not a compound, but it is a molecule. HBr is a compound and a molecule. So you guys have already identified part of this by going through this list. What is the distinction now between organic and inorganic? Hydrocarbons. There are, I would say, a handful of molecules that kind of ride the fence here between being organic and inorganic. And this is a side effect of us as chemists, us as scientists, trying to draw lines in the sand and put nature into nice little boxes. It's not always going to be nice little boxes. Nature is a spectrum, and there's always going to be things that just barely aren't exactly what we'd like them to be. So let's talk about how you guys organized these reagents. I did actually make a mistake in this document. I think that I should have said group the following chemicals and not compounds, because there is a chemical on here that is not a compound. Br2 is on this list. Br2 is a molecule but not a compound. I should have said group the following chemicals. What did you guys put in organic molecule? Give me a raise of hands. Belen? Methanol, CH3OH. Good. What else? Melena? C5H5N. Pyridine. We're gonna work with pyridine this semester. Haley. CH3CO2H. Anybody know what chemical that is? Acetic acid. Vinegar. Good. Anything else? Okay, we can move on, but I'm not going to call on somebody twice. Sorry. Let's talk about what you guys put in inorganic molecule. H2O. Thank you, Max. What else? Not NaOH. Not NaNH2. We're on a roll. Let's identify what those two things have in common and what disqualifies them from being molecules. The sodium. So both of those chemicals have a metal and a nonmetal, or really a metal and a polyatomic ion made of nonmetals. In Gen Chem, we learned that metal and nonmetal creates an ionic bond, and most people won't refer to ionic things as being molecules. They'll refer to them as being ionic compounds for whatever reason. So what did we have? NaOH and NaNH2. No hydrocarbons in those chemicals, but they both have sodium. When you see that sodium, I want you to think of that as Na+, which means whatever else you've got, OH- or NH2-. Did you know that hydrogen and sodium are pretty close to each other? Hydrogen and sodium are in the same family. So why is it that I can't do that with hydrogen? Why can't I look at H2O and think of that as H+ and OH-? Hydrogen's not a metal. which is true despite the fact that it's in the same family as the alkali metals. Lithium, sodium, potassium, all alkali metals. Hydrogen's in the same family, but it's not a metal. Hydrogen technically could also be in the halogen family. It shares some properties with halogens, just like it shares some properties with the alkali metals. Like, it only makes one bond, and it needs one extra electron to fill its outer shell. It's just like a halogen. In the same way, helium is a noble gas, group 8, but helium is also group 2 because it has 2 valence electrons, but no one would say that helium is a metal. Until you get into a star, maybe then you can make metallic helium. So this is something I want you to never do. Plus, why would you even stop there? Why would you break one OH bond? Why would you not break all of them? But this is something I want you to always do. I want you to be recognizing where covalent bonds are and where ionic bonds are. All right, let's fill in the rest. Raise of hands. Yvonne? Where? Good. Did anybody put sulfuric acid somewhere else? Where'd you put it?
I put it as an inorganic ion.
Inorganic ion.
I thought maybe they dissociate.
And we know that sulfuric acid dissociates readily. It's a strong acid. Both of its hydrogens dissociate in water or in something that is basic enough to take it. But in the same way that we shouldn't break this OH bond in water, we also shouldn't break the OH bond in sulfuric acid either. They do have a covalent bond. It's just that that covalent bond is easy to break. Good. Max, I think I saw you raise your hand again.
Oh yeah, NaOCH2, yeah, the organic ion.
Organic ion. This is sodium methoxide. We've got that sodium in there again, so we know it's going to be ionic. We've got a hydrocarbon, so we know it's organic. What else we got? Camille.
SOCl2 in inorganic molecule.
Good. This is a compound called thionyl chloride. We'll use it a few times this semester. We used it once in OChem 1. And I'm going to have you guys draw its structure because it's an interesting structure to draw out. Okay, what else we got? Br2. Where does it go? Inorganic molecule. Good. And then we've got KOCCH3, also called potassium tert butoxide. Organic ion. Is that all of them? Awesome. What did you guys think of that activity? Good refresher? Good way to frame, I don't know why I switched colors, I'm sorry. Good way to frame the types of chemicals that we're going to be interacting with this semester. All right, here's the next activity I want you guys to do. We'll spend probably the rest of the hour on this, the next 10 or 15 minutes. This table in front of you, some of you that were in my OChem 1, do you guys remember this? Raise of hands. Okay. We're a little bit mixed up. I think I'd like for you guys to work, people that have done this before, I'd kind of like for you to work on this with people that have not done this before. What we're going to look at are all of the different common bonding patterns. I told you earlier, I want you guys to learn your ABCs of molecules. These are your ABCs of molecules. I want you to be able to recognize trends in how carbon, nitrogen, oxygen, and halogens bond so that you can quickly identify what charges go with them. You can calculate formal charge anytime you want to. Do you guys remember an equation that helps you calculate formal charge? One more time for me.
Number of bonded pairs minus the number of lone pairs. Non-bonded pairs.
It's that those are two parts of it, but we're missing another part. Lily? That's a part of it, but we're missing a part. Valence electrons minus lines plus dots or sticks plus dots. You may have heard the equation valence electrons minus non-bonding electrons and minus 1/2 of bonding electrons. All that does is give you extra mental math to do. Okay, 1/2 of all bonding electrons. Well, bonding electrons are shown as lines, so I'll have to count the lines, multiply that by 2 to get the number of bonding electrons, and then divide it by 2 to get half of the bonding electrons? I just multiplied by 2 and divided by 2 for no reason. So instead, if you just count every line, you are counting half of the bonding electrons. So I have a former student to credit for this language, but they were the one that gave it to me as dots plus lines. If you have a structure, you just count dot plus lines. We're not going to be bonding these central atoms to anything. We're just going to show dots and we're going to show lines. So let me give you guys an example here for carbon in a -1 neutral and +1 state. A -1 carbon, well, that could be a carbon with a lone pair and 3 lines. The way I've shown it here, those 3 lines are 3 single bonds. Do they need to be 3 single bonds? No. So I could also have a double bonded carbon with a single bond and that lone pair. Or I could have a triple bonded carbon with that lone pair. Here's one thing that I would like you guys to show in addition to just those structures. Just because it's in the line that says -1 doesn't mean I don't want you to show formal charges. So next to those atoms that hold that negative charge, get used to drawing in those formal charges. Did I have it backwards of how I have it on your table?
Yeah, but it's okay.
Sorry. I must have done it differently this semester than when I normally think of it. A neutral bonded carbon, I would be all right with you guys ignoring the radical situations. I'll fill in all of the radicals for you guys when we're done. The radicals are just a little less common and a little bit more confusing. Carbon likes to make 4 bonds. So the way that we make those 4 bonds can vary. 4 single bonds, a double and 2 singles, 2 doubles, or a triple and a single. Those are all situations that give us a neutral carbon. A positively charged carbon, which is upside down on your table. This is a carbon that has only 3 bonds. Now, there are 3 different ways that you could propose this, similar to the 3 ways we proposed the negatively charged carbon. But that triple bonded, positively charged carbon, I've never seen it. I've never seen it proposed. I've never seen it theorized. It's not a commonly shown structure, so we're not going to draw it because it's just not something you guys need to get familiar with. Deal? All right. Collaborate with one another. Spend the next 10 minutes on this, and I'll work on putting my answers up on the board so you can check them when you're done. Is that cheating? Yeah.
No,
Yeah.
I said I won't do it without my notes though. So.
Good. I'm going to encourage you guys later to try doing this again without your notes to see what you can come up with and what you forgot. Do you guys, I didn't tell you what X means. Do you know what X means? Halogens. Yeah. So that's a way of showing F, Cl, Br, or I. All halogens.
Oxygen does a triple bond, right?
We'll see it.
Okay.
Yeah.
Well,
It is rare. Well, actually, Ella, can you draw carbon monoxide? Lewis? Think about it. Try sketching carbon monoxide. You guys were quick.
Yeah, we kind of got a head start on it.
Good.
We thought we were cheating though.
With what?
Her
Just 'cause we
table
had
she
it.
had.
Oh, that is cheating. Yeah. You just copied it?
Huh?
You just copied it?
No, we also, we talked about it.
Good.
There
good.
was mistakes, so we did.
Yes.
Oh,
talk
good.
about it, so.
I had mistakes in the fall?
No, I definitely just copied it.
Oh, shoot. I'll have you guys add a few more too in a little bit.
Figure out when I found the periodic table.
Carbon doesn't have
Nice, Melina.
This one looks kind of cursed.
It does look a little cursed, doesn't it? There's another version of it as well.
Oh, yeah.
Actually, what I want you to notice, and Matthew, you're in a similar spot too, a lot of these bonding structures that you see on your positively charged nitrogen
Yeah.
are the same bonding structures you saw on your neutrally charged carbon.
Okay.
They've got this relationship. What carbon thinks of as neutral, nitrogen takes as positive. What nitrogen thinks of as neutral, oxygen thinks of as positive. What oxygen thinks of as neutral, halogens think of as positive.
Yeah.
I was just going to ask you to do that. Great job. So you guys are on a great start. And think about that relationship, especially you right now. Is there a bonding pattern here that you haven't shown here?
Yes, there is.
What are you thinking, Lamb?
It's been so long since 4 years of organic chem one.
Oh, yeah.
I'm just like looking over bond and lone pair
Good.
to get a refresher.
Good.
But
So the only thing I'd like you to show here is the lone pair. Just for this exercise, show the lone pair on the end. And in this example, you don't have to show what it's bonded to. Just show that nitrogen can make a triple bond. And then you've got one other way. It can make 3 single bonds, it can make a triple bond, and there's one other bonding pattern that you'll see there as well.
Yeah, I think I'm done.
Yeah?
It's really messy because I just wrote like one big one in the middle and actually try to fill in the other.
Oh, yeah. I think actually here, these would not have positive charges.
They wouldn't?
No, it has too few electrons. If we did the calculation on it, 5 valence electrons for nitrogen minus 2 would be a +3 charge,
Oh, +2 charge?
which is a bit too much. Let's work it backwards. If I wanted +1 equals 5 minus what? I'd need it to be 5 minus 4.
Right.
So how am I going to get 4? There's actually a couple of different ways, but 4 lines, that would mean nitrogen is bonded 4 times.
Oh, I see. Okay.
And what we'll find is that all of the bonding patterns of neutral carbon gives positively charged nitrogen.
Okay.
A,
I see.
a negatively charged carbon is a neutral nitrogen, is a positive oxygen.
Yeah, I kind of just went along the lines, just -1 line and just put a little positive sign on it.
Oh, yeah.
Just because I never really learned that. But now I know, so thank you.
You bet. If you want another one, Max, I've got more.
Oh, it's okay.
Okay. All right, a question for you. Can you define a radical? Yes. A radical is represented by just a dot, meaning it's what? A single electron? I heard some other words. Non-bonded electron, as are lone pairs. Unpaired electron. Highly reactive, but not always charged. You'll notice that our neutral lane, each of our elements can be shown as a neutral species holding a radical. If you just take away one bond and replace it with that one radical. I've given just kind of a selection here of what that would look like. I think we can agree that the 4 single bonds from carbon, it could have been a double bond, a triple bond, that became a radical species as well. That's just one example for us. Sometimes radicals can also have charges. We will review mass spec in the coming weeks. Mass spec often uses radical cations to make determinations about molecular weight. That's what happens when, from a neutral bonding environment, one electron is ripped away, one electron remains unpaired. These situations in black, those are the least common situations. They're the ones that you will work with the least often. Everything else in red, you're going to see this semester. So I want you to be familiar with it. My advice to you about this process, this diagram, is to try and replicate this again this weekend from memory. And then look back and see which ones you got right, which ones you got wrong, which ones you missed. Come back a week from now. Try to replicate this from memory. The more you replicate bonding patterns and associate them with charges, the easier it becomes to do so. There was one other thing I wanted to say about it, but I forgot.
Is it that their neutral is their plus? What was that? I know you told me is that their neutral is going to be like the +1 charge.
Thank you. Yes, that was exactly what I wanted to tell you. All right, there is a pattern on this diagram, which is that a negatively charged carbon is in a bonding environment that nitrogen finds neutral. And a neutral nitrogen is in a bonding environment that oxygen finds positively charged. As you move across the periodic table, those atoms prefer more lone pairs, less bonds. If you give oxygen the number of bonds that nitrogen prefers, that oxygen is lacking electrons for itself, positively charged. Negatively charged nitrogen is a neutral oxygen, is a positively charged halogen. Milena said that this looked cursed. It is. I'm going to make you guys draw it this semester as well. It's not a very common bonding pattern, but it does exist, and it explains a lot about some of our reactions. That means that on this diagram, there's really just 2 outliers. There's this positively charged carbon environment and this negatively charged halide environment. Again, I told you guys that there's a third form of that +1 carbon you could predict. It's not going to be common. But I want to ask a question real quick about these 2 structures. You can see that I've done a little bit to show geometry in these drawings. Not super well, but This has a trigonal planar geometry. Those lines are shown in the shape of a triangle, right? What geometry appears to be shown here? Linear. So why is it not bent? Like all of these other things have this sort of bent shape to them. Why are these two lines not shown like this? There's no lone pair. A lone pair would repel those bonding pairs, but there is no lone pair, which means these bonding pairs are repelling each other. They want to repel each other as far away as possible, so they're going to have this linear orientation. That's the process of counting electron domains and using that to predict a reasonable electron geometry. That's what we're going to talk about when we get onto the back side of this sheet. But before we do that, I want you guys to take a quick break. So let's take about 5 minutes and come back in.
Oh yeah, for the outcome review, outside is due September 14th of last year.
When did you check?
It's okay, I said it was
Like yesterday, I was doing the quiz and it still said that, and I checked this morning and it still says the 25th, 0.35. So I don't know when it
Thank you. I'll fix that right now.
The emotes, just the play style of people, like they'll just arrow you in how we're building and just stall it out. Well, you play one, so.
How do you know?
You told me.
Oh, I did?
Last class, yeah. And you play Night Princess, Dark God.
No, I don't. We had the stuff in show back in 2017.
lived on all of them. She lived in Antarctica for a year. For a year. That's crazy. All right. Let's talk a little bit more about bonding, shall we? Valence bond theory. Something that I know you probably learned about in Gen Chem. Those of you that I had in OChem, I know we talked about it, but it's not something that we talk about every day. Does anybody remember how valence bond theory defines a bond? No, but thank you for trying. I'm sorry.
Is that the like Vesper geometry stuff?
It's related, but Vesper geometry isn't bonding. Vesper geometry just says, actually what we were talking about before, Vesper says electron regions repel into the shapes that we're expecting. How does valence bond theory define the fact that a bond exists? What? Overlap. Overlap of? Yes. Sarah, you had another word for it? No?
I just said pi bonds and sigma bonds.
That's true. Actually, it does lead to pi bonds and sigma bonds. And these electron clouds, they get a little bit more defined, right? So valence bond theory says a bond is the overlap of orbitals, whether those are atomic orbitals or hybridized orbitals. So you know what time it is. It's time to review hybridized orbitals. And this is actually going to help us tie back into Vesper and molecular geometry. Do you guys love hybridized orbitals or what?
I actually do.
Yeah, me too.
I like counting them.
Yeah. So orbitals are just math. In fact, those chemistry majors in the room, when you guys get into physical chemistry, you'll have the Calc 3 background needed to derive the equations that describe the electron orbitals. Because that's all that orbitals are. They are just mathematical equations describing the size, shape, and orientation of electron domains, where an electron is predicted to be. And you know how sometimes those orbitals are two parts, shaded and unshaded? That shading is a visual representation of a plus or minus sign at the beginning of the math equation. So the math equations, you guys know the quadratic formula? I don't. B squared plus or minus the square root of the rest of it. That plus or minus part, right? That's an important part. The plus or minus feeds in here. I like to simplify it and just say, imagine that when the electron is in one place, the plus sign, it's just moving a certain way. When it's in the other place, the minus sign tells you it's just moving the opposite way. Maybe it's a little bit more complicated than that, but electrons are super complicated things anyways. So that's simple enough, and it just gives us justification for doing all of this shading and unshading, right? All right, these are the orbitals that we're going to start with the most. S and 3p orbitals. Those p orbitals lie along the cardinal axes. So we can say that this is px, py, and pz. And to show you that these mathematical equations, that these orbitals define size, shape, and orientation, we're going to orient these orbitals along those cardinal axes. Px along the x-axis, py along the y-axis, pz is coming in and out towards you. So if you actually drew it correctly, you wouldn't see the orbital in the back, because that orbital in front should completely eclipse it. But that's not super useful to us, so we just draw them a little bit side by side. What's the shape of an s orbital? Spherical. Typically, you'll see s being unshaded, which might make you think that it's only ever has this one sign that the unshaded parts of the p orbital have. That's not quite true. The s orbital can be plus or minus, but it's all or nothing, whereas p orbitals are both plus and minus at different regions of the orbital. What do we call this part of a p orbital, where that shading and unshading meets, where the orbital doesn't exist? This is a node. Is it odd to you that electrons are able to go from one region to another through a node, which by definition is where the electron has 0 probability of existing? How does it get through a region of 0 probability to go from one side to the other? Is it odd? Maybe. It should hurt your brain a little bit. Remember that electrons are not just particles, just like photons. Electrons are waves. And if I were to draw for you a wave, let's say this is not a wave, and now I have a wave that's doing this. Would you guys agree that right here, I technically don't have a wave? It's level to where I didn't have a wave before, so technically at that point, my wave is 0, which would also be true here, and so on. Electrons are waves, so by having this oscillating motion, the part in the middle means it doesn't exist there because it's even with there not being a wave. That's what this node is trying to represent for us, the wave nature of the electron. All right. If you took an atom with its atomic orbitals, s, px, py, pz, and you tried bonding other atoms to it by overlapping their orbitals, you're going to find that those electron regions have angles of 90 degrees. And they're going to be very close to each other, and they're going to have a lot of repulsion from each other. Atomic orbitals do not set yourself up well. They don't set your atom up well to have minimized strain during bonding. And so instead, these orbitals, as mathematical functions do, start to add and subtract with each other to give new mathematical equations that we call hybridized orbitals. The s orbital is always going to hybridize, but we can do this in pieces. First, we'll hybridize s with just one p. Then we'll hybridize s with two p's. And then we'll hybridize s with three p's, all three of them. Let's look at what this gives us. What should we name the orbital that is produced by hybridizing s with 1p? Okay, I know that's what we have to call it, but what should we call it? Okay, no, I just, do you guys have a better name? I don't either. S kind of makes sense for a fully spherical orbital. S, spherical, I like it. P makes sense for a petal-shaped or propeller-shaped orbital, P, propeller. The orbital that's made by sp hybridization, well, first of all, because I have two orbitals being hybridized, I get two orbitals back out. Those orbitals take this shape. You'll notice that they look a lot like S, but they've got this little nub on one side, kind of like P. They're a mixture of S and P. You'll also notice the orientation. I only hybridized px, which means my new orbitals only have orientation along the x-axis. These orbitals are oriented linear to each other. SP hybridization leads to linear geometry. Linear geometry tells us that we have SP hybridization. I'm left over with my PY and my PZ. Which can be used for pi bonding. They don't have to be used for pi bonding. For example, this is a linear oriented carbon, which means it must be sp hybridized, but it only has one pi bond, while it has a maximum of 2 pi bonds. It's not using its second p orbital for a pi bond. But those unhybridized p orbitals, they're useful in making pi bonds. Let's look at sp2 hybridized. And I'm sorry, that little thought experiment of what should we call sp, I don't know. I don't have a good answer for it either. I think sp conveys a lot of information, actually. It is an orbital that is 50% s and 50% p, but it would be nice if it had a new name. I think somebody has tried to name it before, and they named it like Frank or something, which is not conveying a lot of useful information. sp2, I'll take my s orbital, I'll hybridize it with p and with px and with py. This gives me 3 new orbitals. 3 orbitals in, 3 orbitals out. I now have access to an entire plane, not just one line, not just one axis, but the xy plane, because I've hybridized px and py. Those orbitals want to spread themselves out as far as possible, so they take on this trigonal shape. sp2 gives us trigonal planar geometry. And we're left over with just one pi bond. Notice that I went from saying pi bonds to pi bond. That means one pi bond is possible, but one pi bond is not required. Notice this carbon, which has 3 bonds, 3 electron regions. They're going to repel each other as much as possible, but it has no pi bond. Trigonal planar geometry, it just has an empty p orbital coming in and out of the plane, coming in and out of the plane of the board towards us. All right, the last one, sp3. Some people call these sp squared and sp cubed, which is nice. I like it, but we're not in math. Well, I mean, it is math, isn't it? sp3, all 3 of the p orbitals are hybridized, which means I have access to all 3 orientations of space, all 3 dimensions of space, which makes drawing this actually really challenging. So I'm going to start by sketching out what these 3 orbitals will take on in 3-dimensional space. Right here is the middle where the node meets. 2 of these orbitals will be in the same plane as each other, which we will set to the plane of the board. 2 of these orbitals will be in the same plane as each other, but will come in and out of the plane of the board. So I've got this wedge and this dash. And then drawing those orbitals can look a little silly. Just because drawing that in 3D, I didn't go to art school, and you're not in art, well, you might be in art school, but this is not an art class, so it looks maybe not as good as it could. How many pi bonds can that atom make? None. It has no p orbitals, and p orbitals are what lead to pi bonds. All right, if you're curious, this whole idea of orbitals being mathematical equations that can be summed and subtracted, let's just take an example with the S and the P. Remember that we said the unshaded part represents a plus sign in the beginning of the math equation? So where unshaded and unshaded overlap, you're having constructive interference. That region should enlarge. Where you have plus and minus, shaded and unshaded overlapping, they subtract from each other, which means that I get this big region on one side that is unshaded and this small region on one side that is shaded. Those mathematical equations are just being represented by shapes, and then those equations are being summed and subtracted. So one question I would have for you is, if I do that equation once, why did I get two results? Nobody knows. No, just kidding. I don't know. It's a little hard to explain. It's something about the quantum nature. It's either this or it's that, but actually it's both, so you get both outcomes of the possibility of summing them. It gets a lot more convoluted when you try to show the math to solve for these, so I'm not even going to bother showing you that. But one thing I do want to point out about all of this, I have separated these orbitals from each other so that we can visualize them well. But the node that we talked about earlier, that's right where the nucleus sits. And the node actually is present on all of these at the same spot. So if we were to really draw these correctly, they'd look a little bit more like this. But that just gets a little too confusing to see. It doesn't help us convey as much information. So I like to just separate them a little bit more. All right. Now that we know how atoms can take their atomic orbitals and hybridize them to create hybridized orbitals, now we can start to talk about identifying what hybridization atoms have in a structure, what orbitals they have access to, and what orbitals must be overlapping in order to give us our different types of bonds. Let's start by defining the two major types of bonds, sigma bond and pi bond. Can you tell me how a sigma bond forms? Head to head, head-on overlap of two orbitals. A pi bond, side to side. There are more bonds, by the way. Metals can make delta bonds, which is a face-to-face overlap of d orbitals. It's very fun. D orbitals can also make pi bonds. D orbitals can also make sigma bonds. You scale up the possibility of bonds when you scale up the size of the orbital. All right, let's draw these structures together. HCN. I don't want to spend too much time reviewing Lewis dot structures because we're not going to do a lot of Lewis dot structures. But Lewis dot structures really come down to counting valence electrons, maximizing bonds to less electronegative atoms, minimizing bonds to more electronegative atoms, giving lone pairs to more electronegative atoms. HCN gives us a structure where hydrogen has one bond to carbon, carbon has 3 bonds to nitrogen, and the nitrogen has a lone pair. True or false, hydrogen is S-hybridized. But does it feel wrong?
I feel like it's one more bond.
it hasn't hybridized with anything, right? It's just S. Whereas the carbon and the nitrogen maybe has actually hybridized, changed the shape of its orbitals. So hydrogen maybe is not S hybridized, but it feels kind of consistent to say that. Hydrogen just has S. That's all it has. What is the hybridization of carbon? How did you know that? 2 regions, SP. How else can you know that? It's linear. Although I drew it linear, so that was kind of me handing it to you. I could have drawn it bent. It would have been wrong, but I could have drawn it that way. So the fact that it's linear, SP, the fact that it has 2 electron regions, SP, how else can you know that? There's more ways. It has a triple bond. Let's say that in a little bit of different wording. It has a triple bond. It has 2 pi bonds. The only hybridization that can make 2 pi bonds is SP. On the same hand, basically another way of looking at it, it has 2 sigma bonds. When looking at a Lewis structure, when looking at any structure, every bonding region contains 1 sigma bond. All of the rest of the bonds in that bonding region are pi. So a 3 bonded region, 1 is sigma because it's always 1 sigma. The other 2 are pi. We had 4 different ways to approach this to say that that carbon was sp hybridized. Can you give me a rationale for the nitrogen? What is its hybridization and why? A hybridization, not geometry. SP and why? It has 2 electron regions. A non-bonding region, the lone pair, and a triple bonding region. Good. Hydrogen, nitrogen, sp, and the hydrogen we said is S. It can't be anything else. So let's use valence bond theory, which says it's the overlap of the orbitals, to describe these bonds in a little bit more detail. What orbitals need to overlap for H and C to constitute a sigma bond? I heard somebody over here. Raise your hands. It makes me easier to call on you. Is that you raising your hand, Katie? Oh, okay. What orbitals have to overlap, Elliot?
It's just S and S, right?
Not quite, because carbon doesn't have an s orbital. Jackie?
Is it between S and SP?
S and sp. Remember, carbon is not this anymore. It's this. It has 2 sp orbitals and 2 pi. It has no s to overlap with. But is the carbon overlapping with one of its hybridized orbitals, sp, or is it overlapping with one of its p orbitals? Well, it can't be a p orbital because that needs to be used in the pi bond. So this bond is the result of s overlapping with sp. What orbitals are overlapping to create the sigma bond between carbon and nitrogen? 2 sps. Sp to sp. Now, if you weren't sure there, we actually took the hardest gamble first. The easiest place to start would have been identifying the bonds needed for the pi bonds. The pi bonds result from this side-to-side overlap. That's only going to happen on p orbitals, which means that these 2 pi bonds are the result of a p to p overlap and a p to p overlap. If you knew that carbon was sp and both of its p orbitals are used up, then the sigma bonds must be using carbon's sp orbitals. This is valence bond theory. Identify the hybridization and then use that to identify what orbitals are overlapping. So I'd like you guys to take the challenge now with the rest of them, draw out the Lewis structure, identify hybridizations, and then identify the sigma and the pi bonds. If you can, start reporting what bonds are overlapping to get you there. I don't want you guys to get stuck on drawing the structures, so if you get stuck on one of them, let me know and I'd love to come over and help you. Oh, and feel free to collaborate. This does not need to be an individual assignment. I'd actually prefer you guys to work with each other.
Oh, I don't know about this one. No, I don't know about. Well, but the thing is though, oxygen only makes 2 bonds. That would make oxygen have a plus charge, and you don't want that.
Yeah, if you need help with any of them, I can see. Yeah, the carbon is just 2.
Oh no, that's.
Good work, Katie. That's the toughest one.
Good.
Hi, welcome. Do you want a worksheet? We're doing valence bond theory. Good try here, but this subscript 3 outside of the parentheses says that 3 of these groups are all connected to one central carbon. So you notice how you got one CH3, but then this is a CH2, right? Good, great.
I have a question.
Yeah.
So I've been evaluating, like for example, on this one, I feel like there is sp2s based on the electron regions that they have. Like this one, the carbon and then the oxygen. However, what I'm trying to wrap my head around, do we consider that the hybridization, like the hybridized orbitals, are also the ones that contain the unpaired electrons?
Yes, so actually we didn't quite do that with nitrogen, right?
Yeah.
Nitrogen, we said, is sp hybridized.
Yeah.
One of its sp orbitals makes the sigma bond to carbon. Its 2 p orbitals make the pi bonds to carbon. Where's the other sp orbital? It's holding the lone pair.
Okay.
Same with oxygen in the formaldehyde case.
Yes.
sp2, it uses one sp2 to make the sigma bond. It's only pi to make the pi bond. Where are the other two sp2 orbitals? Holding the lone pairs. Yeah, I'm gonna actually, now that you reminded me, I'm gonna mention that.
Okay.
Good job.
Yes, thank you.
Your, your structure here is close, but we will actually have both hydrogens bond to the carbon. And that's going to give us a bit of a different bonding structure that's beautiful. Good work. Great job, Matthew. Good. Great work. That fixed it, right? In this one, the sulfur and oxygen are actually going to switch. Sulfur will be in the middle, bonded to both chlorines, and the oxygen will be double bonded to the sulfur.
But what determined why is sulfur but not oxygen?
Electronegativity determines it. The idea that sulfur being less electronegative is willing to make more bonds. Oxygen, more electronegative, wants to make less bonds. If you did the formal charge calculation on oxygen here, you'd find it to be +2, which is not great.
Electromagnetic move up, right?
Electronegativity increases to the right and up, fluorine being the most. Yep, you bet.
Just to clarify, the electron pairs can also be electron cloud region.
They can,
Yeah.
yes.
And is this structure right?
It's really close. The sulfur actually has a lone pair on it.
Oh, what is this then? Oh,
Um,
SP3.
It's actually sp3d.
D.
That's what I was wondering.
It's a weird one.
3D.
It's an outlier for sure. Does. Expands its octet. Did you grab one?
No, I looked at it though.
Okay. Oh, that's why it's flipped upside down.
Yeah, I was telling Al I was doing it. I don't know.
We didn't do it a ton, so.
Well, that's probably why. Even the bonus question on the term with like the
Frost circle.
where you that I got wrong. And
Oh.
the one where you like rank the
Oh, yeah.
I just like memorized that. I had no idea.
Yeah.
I don't know why.
It's just nodes, right?
You were on the board.
All right. These are the structures. Depending on how detailed you wanted to get, the CH3, 3COH, tert butanol, you could draw all of those CH3s out. You could kind of condense some of them if you wanted to be a little bit less detailed. The thionyl chloride, SOCl2, that's a challenging one. Sulfur breaks the octet rule. By being in the third row, it can actually access its d electrons. Using Ella's method of counting electron regions to figure out hybridization. Oh, I guess I was wrong before when I said it was sp3d. And I don't know why I said that. It's still sp3. But it's sp3 with a pi bond. I guess actually we can't use the counting rule here. Sulfur is weird, so I'm not going to have you talk about the hybridization of that sulfur in class, but I did want to have you guys look at the fact that sulfur expands its octet and draw it out. So let's take formaldehyde up here, and let's use this as another good example of hybridization. What is the hybridization of my carbon in formaldehyde? sp2. A few ways we can get there. 3 electron regions, spp, sp2. Also, it has just 1 pi bond, which is characteristic of the sp2. 3 sigma bonds, 1 pi bond. What's the hybridization of the oxygen? Also sp2 for all of the same reasons. What overlap creates the sigma bond in formaldehyde? sp2 to sp2, the hybridized orbitals overlap. What overlap gives the pi bond? P and P. A good question came up earlier. Nitrogen has 2 sp orbitals in hydrogen cyanide, but we only talked about one of the sp orbitals being used to make the sigma bond. What is the other sp orbital doing for nitrogen? Is it empty? Do you want to share it?
Basically, the unpaired electrons are occupying it.
Good. That other hybridized orbital holds the lone pair electrons. We'll see the same thing here. Carbon has 3 sp2 orbitals. One of them is used for the sigma bond to oxygen. Another one is used in the sigma bond to hydrogen on both sides. That's all 3 of carbon's sp2 orbitals. But what about oxygen's? Oxygen used one of its sp2 orbitals, its only p orbital. Where are the other 2 sp2 orbitals? They hold the lone pairs. These 2 lone pairs are sitting in orbitals, the hybridized orbitals, the leftover hybridized orbitals. Valence bond theory is a lie. It's a good approximation, but it's not totally accurate. So when we come back, because I wish I could keep you longer, but I won't, we're going to talk a little bit about molecular orbital theory, MO theory, which is mathematically just better than valence bond theory. But visual representation-wise, MO theory is very challenging. We're going to use this same concept of summing mathematical equations and subtracting mathematical equations to help us predict new orbitals that define our bonds. And MO theory will also help us understand why bonds break. Valence bond theory, if I'd show you this structure, can you tell me why would any of those bonds break? No, not really, just that they will. MO theory will give us a foundation to understand why and how bonds break. Have a good weekend, guys. It's a holiday weekend, but we are meeting on Tuesday. I'll see you then.